This is a lecture in Climate and Earth 440, Meteorological Analysis Laboratory at the University of Michigan. It will be an introduction to the Unified Forecast System. The outline of the talk is as follows. I'm going to give some background, which is going to focus on the culture of the U.S. science enterprise, as well as part of that culture, U.S. science policy. The reason for this is I think it's interesting. It's potentially interesting to students in the long term, potentially useful for students to understand. It is also a major motivation of the genesis of this idea of the Unified Forecast System. Then there's going to be a section on what is the Unified Forecast System. Then I'm going to have some specifics, one being a case study of a particular storm back in October of 2021, and another will be a more general introduction to subseasonal prediction. Then I'll provide a summary which will include ways that students can get involved with the Unified Forecast System activity. For more than 20 years, the U.S. operational numerical weather prediction capabilities have been the subject of public criticisms. These criticisms are two primarily: that the forecasts are deficient to those of the European Center for Medium-Range Weather Forecasts, ECMWF, and that the forecasts do not provide the U.S. with what it has paid for to provide state-of-the-art protection of life and property. Is this criticism justified? I would say yes and no. I wrote an analysis in the Washington Post about the European Center and what it would take to be the best in modeling, a number of years ago now. And I think what I wrote in that still stands today, though we have made a lot of progress with the Unified Forecast System. And I think what I wrote in that had been true 10 years earlier when I was managing at NASA. Therefore, these are chronic and persistent and very difficult problems to overcome. The criticism has been focused primarily on the medium-range forecast model, and in particular, the global forecast model. Medium range is from 2 to 3 days out to 10 days. An important aspect of the thinking about the problem holistically is that this is really only a part of the information used in forecasting. And that's especially true in the United States, where I'll show later that we have 7 applications that we try to address in our weather or environmental prediction. Another consideration to think about is that for professional forecasters, model information is used as guidance. It is only part of the knowledge suite. A real professional forecast is not made by somebody just reading what a single model tells you is happening with the storm. Forecasters view the model as guidance. Another consideration, which is perhaps more interesting from a social science perspective, is if we have forecasts that are, say, as good at 7 days as they are at 5 days now, do we effectively know how to use that increased skill? Some people probably would benefit from that, and many people, those looking at weather forecasts from day to day, probably less so. But objectively, I would say that the U.S. benefits from excellent and improving weather forecasts. Our forecasts include severe storms, hurricanes, storm surge, air quality, and space weather. Also point out that since the U.S. has a global reach, we have interests that require global forecasts that are good all over the planet. Objectively, also, the suite of models that are used in our forecasting system is too complex. The cost of our forecasts is too high, and the model guidance is not as good as it could be. So the Unified Forecast System was proposed after several external advisory panels to NOAA called for 1. Developing a community-based approach to improve the benefit to operational centers from the broader research investments. The Unified Forecast System was also proposed 2. To address known scientific deficiencies. We needed to strive for scientific excellence. And in many cases, these deficiencies occurred because the models were not being updated as fast as, let's say, our competitors are. And our competitors, aside from the European Center, also include the Met Office, the Australian Bureau of Meteorology, the Japanese, the Korean Meteorological Services. We also, more and more, have commercial interests in weather forecasting. There was also a need to address known computational, and I will say information technology infrastructure deficiencies. There was a desire to reduce the complexity and the cost of the operational suite. That will become more clear during this talk of what I mean. And this sort of interesting idea for a scientific enterprise that we needed to adhere more to evidence-based decision-making and system development. What's my role in this? It's not that I'm an expert in weather prediction, because I'm not an expert in weather prediction. But I was asked to take on this leadership role as a special request to the late Bill LaPinta, who was then the director of the National Centers for Environmental Prediction. And I was asked to take this role because of numerous successes earlier in my career in the management of large scientific organizations. I focus on systems. I have knowledge of organizations. I value strategic goals and the management to achieve those goals. And I have been described as somebody able to execute bureaucratic aikido. But to be clear, the deficiencies in the U.S. weather modeling are related first and foremost to organizational issues which lead to fragmentation of efforts. This is at the core of our scientific culture. It is supported by our science policy. There are political interests intertwined with our science policy, and those political interests are at very many different levels. Individuals and institutions are in fact invested in the fragmentation and have set themselves up to sometimes use that fragmentation to their advantage. Therefore, this is an enormously difficult problem that is far more of a social problem than it is of a technical or scientific problem. So with that introduction, I want to make a shift to the unified forecast system. After a couple years of planning and pre-work, and that pre-work involved making some pretty hard decisions, the unified forecast system was initiated, in my accounting, in the winter spring of 2018. That is when the UFS steering committee first started to convene. There were a set of defining decisions. The biggest one was this decision to go to a new dynamical core. And that decision was made in a very arduous and rigorous process that involved multiple institutions across the country. Adhering to that desire for evidence-based decision-making was determined by a validation plan, which was published in advance, which all the parties who were involved in it worked to meet the criteria set out in that evaluation plan. And after that process, the finite volume, non-hydrostatic, the FV3 dynamical core, was chosen for the global forecast system. And this was a dynamical core that was in operations at GFDL, the Geophysical Fluid Dynamics Lab, and it also had a heritage reaching back to NASA Goddard, as well as it had been used and tested extensively at NCAR, the National Center for Atmospheric Research. A decision was also made to have a modular, community-based systems architecture for the coupled model. This architecture followed after many years of investments by several agencies in the development of coupling infrastructure. The decision was also made to adhere to a set of infrastructure decisions, which included that coupling infrastructure from ESMF and NOAA. ESMF being the long-lived activity called the Earth System Modeling Framework. There was data assimilation infrastructure, which was being developed in a program known as JEDI, which was under the auspices of the Joint Center for Satellite Data Assimilation. There was an agreement to use the Common Community Physics Package, the CCPP framework for atmospheric physics, and an agreement at that point in time to also use an analysis package called MET+, which was being developed and is still being developed at the National Center for Atmospheric Research and the NOAA lab in Boulder under the auspices of a program called DTC. A very important aspect of what happened is that there was a first-of-its-kind agreement between NCAR and NOAA on especially these development of infrastructure and some of the services associated with the modeling. Part of this reason was their experience in community modeling. There was a commitment to systems-based planning, and there was a commitment to continuity in planning. And what this was meant to address the fact that there had been a lot of plans, but no one was really following those plans from 1 year to the next. So there's a certain necessity of persistence and continuity in building that needed to be accomplished. After some deliberations, we came up with there being 7 UFS applications: medium range weather, subseasonal to seasonal, hurricane application, short range weather convection allowing application, space weather, coastal, and air quality. The medium range weather application does have a very central role. The global medium-range weather receives the greatest attention because all the other applications rely on the performance of the global model. Historically, this has been the atmospheric model. However, we are moving to coupled models where we're coupling atmosphere, ocean, land, sea ice, aerosol, and composition because we know, because other centers have been out in front on this, as well as the research community, that even on scales as short as 5 days, and arguably even on scales as short as 2 and 3 days, there are important benefits from coupled models. 2 other applications that receive a lot of attention and would be of special interest to this class, I'm sure, are the short-range weather convection allowing and the hurricane applications. The short-range weather convection allowing application is the one we use for tornadoes, derechos, extreme thunderstorms, fire weather. These are forecasts of 1 to 2 to 3 days. Use them for aviation as well. The hurricane application is obvious, a set of models especially focused on hurricanes. And all of these might be called regional or mesoscale models to the students in this class. So what's an application? I think it's important to appreciate that an application is more than just the model. The application has these parts. It has pre-processing and data assimilation. It has the model, has verification and validation, post-processing. There's a workflow that has to manage all of these things, which will be likely different for each application. And then there's a computing and collaboration environment if we're going to be aspiring towards community modeling. So all of the parts of the system are important. There's nothing here that can be neglected and you expect a good outcome of a good forecast. Part of the problem in our science culture is that some of these parts attract more attention. They're more glamorous, perhaps, than other parts. And therefore, we do not have balanced development and balanced resources across these different parts. I will also add that I'm not talking a whole lot about the computing aspects of this, but one of the biggest challenges we do face in the United States is that we do not actually have enough computing that is effectively and efficiently focused on this problem. If you were to look at where the greatest improvements would come from at this point, they're probably going to be, and most people would agree, in data assimilation, better use of the observations that we have to initialize the forecast models. I also want to point out that down here on the model forecast, it said that part of it integrates the model or an ensemble of models forward. This idea of ensemble forecasting is true for all of the applications going into the future. And the idea of ensembles is illustrated here because it's a way to explore uncertainty space. And it gives us a probabilistic guidance rather than a single, what has been called deterministic forecast, which is what we're perhaps used to when we say the weather forecast. That idea is demonstrated here, where in the initial condition you might say you have an observed Gaussian distribution of temperature, and you let the ensemble go forward. You'll see that some cluster, but there might be members of the ensemble going out to these two extremes here. The forecaster is going to look at those, what we might view them as outliers, and say, what are they telling us about the environmental conditions that we need to think of in our modification of the model guidance in order to get a good forecast? So what is the UFS? The UFS is a community-based, coupled, comprehensive Earth modeling system. This system includes the code, governance rules, the community of individuals composed of researchers, developers, and users from NOAA, educational institution, federal agencies, and the private sector. The UFS is designed to support the weather enterprise and, if successful, to be the source system for NOAA's operational numerical weather prediction applications. Since I'm talking with students, or even general public, and oftentimes other scientists, I want to emphasize that forecast is providing guidance. If you go look at NOAA web pages, you can Google numerical guidance, and you will get this sort of definition and this flavor of how forecasters really think of the models as guidance. So numerical weather prediction model forecasts do not define the forecast as issued by the Weather Service. The model forecast, again, provides guidance to the forecasters, and there's a lot of model information available on the web, and a lot of people read off model simulations and call them forecasts. I would say that compared to the professional forecasters who assume the responsibility and the heat from issuing forecasts, they do not just read off what the models are saying. They are considering the models in an extraordinarily complex and time-critical evaluation of information from several sources. I attempt to represent those sources here. We have the global models. In addition to the global models, we'll have process-specific models, for instance, the hurricane models or perhaps a storm surge model. We'll have some observations that are coming in as the forecast is evolving, or we'll have observations that are additional to the ones that were used in the initialization, observations that forecasters know are, say, of special importance to a severe storm prediction. We have theory and expert interpretation, where the theory is going to be things like you learn in class. Is the behavior of moisture and precipitation consistent with temperature and the moisture sources and sinks that are actually in your local environment? And then expert interpretation of, what does the lake at the edge of town mean to the forecast that we usually have? Local information, as well as things like snow algorithms, are notoriously complicated and very, very difficult to put into a model. There's expert interpretation on, what do the real environmental factors mean to things like rain, sleet, freezing rain, and snow. All of this gets into the post-processing and the interpretation, where the post-processing is perhaps viewed as a formal process for correcting errors for a local environment, interpretation, and this is really all focused on exploring uncertainty and managing uncertainty from all of these different sources, because as good scientists, you know that all of these have significant uncertainty associated with them. And then After this, we get the communications, the forecasts, and the watches and the warnings. So this is how model guidance fits into that system. A little bit of a change here. What is the scope of the challenge that the UFS is facing? And this is known as the rainbow diagram. I'm sure there's one that's a little bit more current than this. It's a time series. It's a management diagram. On this side is FY20, fiscal year 20. On this side is fiscal year 25. So we're actually somewhere along in here. What's over here in the red is how many systems are being run today, or how many systems were being run when this plot was made. To be brutally honest, this has already been reduced from what was the case when we really started this effort. And over here, how many systems we want to be running in 2025. And I would say at this point, as we're evolving somewhere in here, we're even starting to think of things like air quality, and others can actually be made sort of an integral, interactive part of the medium range and the local systems. But what you see here, here's a bunch of local systems being unified into one. Here, a less rich number of medium range systems being unified into one. And very importantly, in this one, I'll point out GEFS, which is the Global Ensemble Forecast System. There are also the short-range ensemble systems down here. So there are ensembles coming up everywhere. And by ensembles, we mean we're going to be taking a model and we're going to be running it with different initial conditions and initial start times. And another way we get ensembles is taking models from the other centers and looking at what they're telling us about the forecast. We've had first order of improvements in medium range forecasts, and there's more to come. We have first order improvements in global ensemble performance. We've included the ocean wave model in aerosol, so we're seeing the coastal and the air quality applications getting directly integrated into the global models. We've seen substantial progress on the simplification of the short-range weather convection allowing. And we have recently transferred the space weather, ionosphere, plasmasphere, electrodynamics modeling for using the whole atmosphere version of the GFS into operations. So now I want to show some specifics. I want to focus on the global systems. I hope to demonstrate how model forecasts inform the forecast process. I want to suggest how experts might use model forecasts as guidance to describe and manage uncertainty, fully cognizant that I am just an observer of this process, and I'm not personally an expert. Just to be clear, in what follows, GFS is a forecast system, the global forecast system, branded by NOAA, which includes modeling and assimilation. And as of GFS version 16, the medium-range weather application is used as the model component, and that's been developed by the community of the UFS. So what I want to look at is one storm from 2 October bomb cyclones of 2021. And in particular, I want to look at this one. It was on the west coast. And what you see here is the coast of the United States and Canada. This is out over the Pacific Ocean. This is a trace of the sea level pressure of this system. So a bomb cyclone has to minimally have 24 hectopascals deepening of its central pressure in a 24-hour period, with some details based on the sign of the latitude here. But for this system, you can see here there's been a 46 hectopascal in 24-hour deepening here. From here, there's a 54 hectopascal deepening in 36 hours. So this is an enormous storm that had very explosive growth. If we look at this storm in other ways, this is over here on the forecast side. This is on the On the verification side, perhaps, one of the important aspects of these storms are they have these atmospheric rivers associated with them. And in this one, you see the total precipitable water showing this atmospheric river, this immense amount of water coming into the coast in California, Northern California and Oregon. Over here, something called the Atmospheric River Forecast Index, and you can see that this atmospheric river index had these reds here on the coast, and then all of this water on the inland part, and then over here what we might consider the verification. This is accumulated precipitation over 24 hours, and in this part in here you're seeing 5 to 15 inches or more accumulation of rain. So this is a big event coming, interestingly, after very extreme drought. These extremes at this point are undoubtedly more extreme, both wet and dry, due to the accumulation of heat in our warming climate. So here's another view. Here's the storm. This is the wind up at 250 hectopascals. The central pressure at this point in time is 943 hectopascals here. And for you dynamic students, here's the vorticity at 500 hectopascals. So what I want to look at here are two forecasts, one coming from the GFS, so this would be using the UFS Medium Range Weather app, and then one coming from the European Center for Medium Range Weather Forecasts. What's shown in this figure, these are different forecast times, so each trace of a blue line is a different forecast line. The black is the observed mean sea level pressure traces at the center of the storm, so they're cyclone following. What you see up here is from days 4 to 9 and days 5 to 9, we're not really predicting this storm. However, starting at day 4, the European Center system starts to trace the storm pretty well. Starting at day 3 forecast, the GFS, the UFS-based system, starts to trace the storm quite well. Here on these figures, I'm going to be showing in this corner the GFS analysis. So this is the verification. This is the answer you should get. This is what was on the top left a couple of view graphs ago. And they're going to be forecasts from 3 systems. So this is the European Center system. Here is the GFS system, and then here is the Ensemble system using the GFS model. This is a 6-day forecast, and as you recall from the previous figure, none of the models did this forecast very well. So if we go forward, in this case, a day to the 5-day forecast, you will see again that the models are not doing that well. Now, when I hear the forecast discussions, one of the things they point out, well, here the GFS is behaving a little bit differently, and putting this center down here, which you might argue, looking here at this analysis, might have been a good thing. But we look at that and we go, what are these different models telling us? If we go forward one more day, we note that the models essentially separate here, with the European Center giving this type of explosive cyclogenesis down here. With the benefit of hindsight, this is a noted jump in quality because here's the verification. You can still, from the details of a forecast, argue about the depth, you can argue about the location, but at this point in time, again in hindsight, you would say the European Center model has done a very good job on this forecast. So you have all these sources of information, and it depends on how you weigh them into what you're saying. But then here, one day further on, note that the GFS as well as the Ensemble show this notable jump in quality, again in hindsight compared to this. And in fact, if you look at all 3 of these together, you're now seeing this information converge, and we're becoming quite a bit more confident that the guidance we get is good. One thing to always note about the Ensemble, since it's an average of a bunch of simulations, it's going to tend to be smoother. So you are using the Ensemble really in a different way than you're using these high-resolution simulations, which would be the traditional deterministic forecasts. We saw that. Can we figure out something more substantive? So now I'm going to look at another series of figures of just GFS model forecasts. Remember that the day 4 and the day 3 forecasts were a substantially different quality. So we're going to look at two forecasts initialized 24 hours apart, and I want you to note the role of the short wave. So those of you who have had dynamics should have been introduced to the concept of long waves and short waves in mid-latitude cyclones. These are the types of figures we're going to look at. On this side of the figure is going to be the forecast initialized 4 days earlier. On this side of the figure is going to be the forecast initialized 3 days earlier. Down here, this will be what it should look like at the time of this forecast. The initial time of the forecast is here. So you can see here 1021 forecast, 1020 forecast. The forecast time, so at this point in time, this is 24-hour forecast. This is a 0-hour forecast, so this is the analysis. So these two are actually identical at this point in time. So we go forward 12 hours, and what I want to point out is this wave here that is circled in blue. If you were to look carefully, and you can look in class or magnify the screen when you get the opportunity, you'll see that the shape of this little wave is different between these two simulations. And if we go forward another 12 hours, so we went from 24 to 36, you'll see here's this little wave here, right there. Again, you can see qualitative differences here. It's a little bit deeper, perhaps a little more symmetric. And if we go forward to a 48-hour forecast, then a 60-hour forecast, and then the 72-hour forecast, which is when this bomb is supposed to have happened, you'll see here in the 3-day forecast, this has really wound up, whereas you don't see nearly the intensity that you saw in the 4-day forecast, and these were seen in the previous figures as those two-dimensional plots. And in this case, the forecasters doing this sort of analysis after the fact, which is one of the ways you start to understand what's going on in the models. You could say that both the GFS and the European forecast delayed the formation 5 to 8 days out, so they did not suggest this 5 to 8 days out, so it was producing much weaker cyclones than analyzed. The European Center captured this, gave us some warning of it at day 4, and that appears to be due to better handling of this short wave, this 500 hectopascal geopotential height pattern, as well as the cutoff low on the Washington and Oregon coast. The GFS forecast did not capture this until the 3-day forecast. Once the two of them come together, you get a lot more confidence, and it's very likely that the representation or the misrepresentation of that short wave is probably more of a problem of data assimilation, data selection, than it is of model performance. And you'll note here the Ensemble system struggled to forecast the West Coast cyclone until day 4 and did not capture the timing in its formation until day 3, very similar to the GFS. Perhaps you would expect it to reflect the performance of the GFS. Role of models. My purpose here was to demonstrate that the differences between model forecasts are used to explore and describe the uncertainty. They provide context. Some models prove with sufficient statistics to be more reliable than others, and in the medium range, I don't think anyone would argue that the ECMWF model verifies with the highest skill. There has been substantial reduction of the gap between the U.S. models and the ECMWF models for many situations in the last 2 to 3 years. The regional and process models contribute to the uncertainty exploration close to the forecast time. They bring information that's unavailable from the global models. They often provide improved model forecasts, but sometimes they do not because they do not capture the global situation as robustly as the global models do. So all of these models are bringing really different flavors of information that experts then evaluate in the generation of a forecast. So I'm going to do a quick shift to the problem of subseasonal prediction and the motivation for subseasonal prediction. One of the things that we've noticed over the years, is that the atmosphere has these modes of variability. They're called teleconnections. They're related to the structure of the jet stream. They're related to ENSO, the El Nino Southern Oscillation. We can show that there are relationships between what's going on in the stratosphere. We get these things that are called often persistent anomalies like cold air outbreaks or heat waves. We get floods associated with atmospheric rivers, especially if, as been going on for like a month now in British Columbia and Washington, just one atmospheric river after another. And then where it's not raining because it's hot, we get drought. A lot of these things are related to blocking, which is a very difficult process to simulate. Really, almost all these processes are related to long waves or Rossby waves in the atmosphere, and many times coherent or incoherent interaction between different types of Rossby waves. So in here, this green is the jet stream. What I want to just give a little bit of focus on is, we've noticed that these different modes of variability often tell us something about what's going to happen 2, 3, sometimes even 4 weeks in advance. We've also noticed that if we can understand that the atmosphere is going to get locked into one of these patterns, that we can have long spells of, let's say, rain or drought. I want to spend a little bit of time on one that I'm just beginning to learn more about, the Madden-Julian oscillation, which is convective systems that propagate along the equator, and they have different phases. And this one I've put as MJO, Madden-Julian oscillation, phase 1. I think the experts put it in 8 phases as it propagates from the western Indian Ocean across into the central Pacific. Here's phase 1, phase 2, phase 3, and then it continues on through phase 8. One of the things that I think is very exciting is that if we look at in more detail, say, the Madden-Julian oscillation, and in this figure, what you see here is Asia, the Pacific, North America. This green here is the precipitation of the Madden-Julian oscillation in its phase 3, in its Indian Ocean location, really on the more eastward side of the Indian Ocean, getting over towards Southeast Asia and Indonesia. And so here's MJO here. What we see is that these very coherent wave trains often occur with MJO3. When we get this strong wave train, which is hypothesized to come from the wave being generated by the Madden-Julian oscillation coming into coherent interference with the standing Rossby wave here, then we get these very strong wave signals. And during these times, if we can see one of these things coming as the Madden-Julian oscillation propagates along, this is a time when we see, say, big atmospheric rivers coming into this part of North America here. So this is the sort of motivation that is really driving the desire to see what sort of predictability is in this subseasonal range. And this is where a lot of the activity in the field is at this point. So in summary, the UFS is a cultural change in how the U.S. is addressing the operational environmental modeling. There has been substantial progress with improved forecasts, Initial simplification of the modeling suite. We have addressed some issues of cost. There's still major computational cost challenges, and there's been far more engagement of the forecaster community with the model development community. There's much left to be done, and continuity must be maintained. That is, we need to build off successes. We have to actively fight the organizational inertia that promotes fragmentation. We have a big infusion of new capacity that we are currently trying to integrate in with the UFS activities called the Earth Prediction Innovation Center, EPIC. One accomplishment is that the code is far more accessible, and this is because of the adherence to something called the graduate student test, which was posed some time ago, that a good graduate student should be able to download, modify, and run the code from the systems, and they should be able to do that in less than 6 hours. And we have accomplished that with both the medium-range weather application and the short-range weather convection allowing application. There are also many NOAA opportunities. I will specifically mention the LaPinta internships because Bill LaPinta was really a driving factor about the actual implementation of the UFS. There will be a lot of UFS activity, including there should be some UFS activity at the Student Symposium of the American Meteorological Society meeting. So with that, I'll just show that I have some references here. Here are some basic references on the UFS, some basic references on the model evaluation group, which is where you can see the official evaluations of the systems that go into operations. They are amazing meetings. And then some references on subseasonal to seasonal. And then I will go back to the graduate student tests and the LaPinta internships and say I'm through, and thank you for your attention.